All right, today's lesson is going to be on least squares regression lines and residual plots. So we're going to learn how to make a new type of plot today that gives us a little bit more insight about how good of a linear fit a least squares regression line is. All right, so numbers 1, 2, 3, and even 4 are kind of review. So I'm going to give you a second. I'm going to pause the video. I would like for you to complete numbers 1 through 4. And when you're ready, unpause the video and see how you did. All right, let's see how you did. So we've got data of all iPhone sales during the opening week, okay, in these years. And then, of course, the sales is Y. So we should have graphed this, and your graph should have looked something like mine. Notice I labeled list 1 and list 2. That's where I put my data. X in list 1, Y in list 2. I labeled year and units sold. It said describe the form of the distribution. Remember when we talked about form, we said linear or nonlinear. This does not look linear to me. It looks like something possibly exponential, but there's definitely curvature occurring. I ran the linear regression and got the equation y hat, don't forget the hat, that means predicted, equals negative 3,222.63 plus 1.605x. Part 4 says use the least squares regression line to calculate the residual for 2007. That means I plug in 2007 into the regression equation to get out the predicted sales for that particular x value. The residual is calculated as what we actually observed minus what we expected. So y minus y hat. The actual y value for 2007 was 0.5 million. So I plugged that in for what we actually saw occur versus what we expected to occur, which is a negative 1.40. 0.5 minus a negative 1.4 is 1.9. So the actual number of units sold in 2007 is positive 1.90 million, greater than predicted. Okay, so now what we're going to do is we're actually going to complete this table below. You can do this by looking at all of the predicted values and plugging each one individually into the equation. We just did the first one here. For 2007, we plugged into the equation and we got out negative 1.40, and we found a residual to be 1.9. Okay, however, plugging into our calculator every single time doing this process could be a little bit tedious. So what we can do is, if your data for X is in list 1 and your data for Y is in list 2, in your calculator, at the very top where you see the list, I'm going to just come over here and show you, for example, where it says list 1, list 2, list 3. Take your cursor, put it on top of list 3. And what you want to do is you want to enter the equation. Okay, you want to enter your equation, which your equation is negative 3,222.63 plus 1.605. But instead of just looking at one x value, we want to plug every single x value in. So that x value of 2007, I want it plugged into this equation. That x value of 2008, I want it plugged into that equation. So what I can do is, instead of writing x right here, I can insert list 1. And what your calculator will do is it will immediately do all of this multiplying for you. It will take this x value, plug it in, and give you the answer. This x value, plug it in, give you the answer. The next x value, plug it in, and give you an answer. I'm going to give you a second to work with your calculator and then unpause the video and come back. So this is what I mean. I went ahead and highlighted list 3 right here, typed in, while I was still highlighted at the top, typed in this equation, but instead of x, I put list 1, and now your list 3 should look something like this. Those are all of our, oops, sorry, I want that out of the way. predicted values. So we can go ahead and copy that over here if we want, just to show that we calculated them all. Of course, you could totally plug them all in by hand if you would want. I don't know why you would want to do that. So here's what we should have had in that table. And this should match what you just got out. Okay. And of course, these values came from list 3 in our calculator. Our calculator should help us work smarter, not harder. And 11.44. All right, to get the residual, that is y minus y hat. We did that before, right? We took the y value, we subtracted the y hat value, we got 1.9. I can do that for every single one. This value minus this value equals this value. This value minus this value equals this value. Or in our calculator, in list 4 now, when you have it highlighted on the top, just like before, you could enter list 2 minus list 3, because list 2 is where all your y values exist, minus list 3 is where all your y hat values exist, and the calculator will do all that math for you. Why don't you pause this video and give it a try? Okay, so in list 4 of your calculator, you should have these values there. Those are your residuals, okay? And your calculator is just a shortcut for how we can get those, but it doesn't necessarily mean you have to use the shortcut. You could plug every single value in by hand, just like we did for equation or for step number 4, but it just is a little bit time consuming. Now, step 6 says graph the residuals on the axis below. This is the residual plot. We are actually going to make the residual plot now. The residual plot is always on the y-axis, the residuals. That is the vertical distance from the line of best fit to what our actual observed values were. And the x-axis is always right there, which is the year. All right, I'm just going to go ahead and plot these by hand. So the first value I have at 2007 is a residual of 1.9, 2008, 0.79, 2009, I've got negative 0.81, 2010, negative 1.72, 2011, negative 1.02, 2012, negative 1.63, 2013, I've got 0.77, 2014, 0.16, and 2015, 1.56. One thing you should notice about the residual plot is that all of these values up here show us when the actual value is greater than what is predicted. So the actual is greater than the predicted. These points indicate in underestimation, okay? Down here, all of these points are where the actual is less than what we predicted, okay? This indicates we did an overestimation. So for question number 7, it says, for which points was the actual greater than the predicted? I'm just going to go ahead and highlight those on my graph right now. So the actual greater than the predicted here. And it says, for which points were they less than predicted? Here. Okay. And we just identified those on the graph. And right here it says, do you think the regression line is a good fit for the data? Why or why not? Explain using the residual plot. Okay, a residual plot gives us a lot of information about an actual graph. I see these points were above the line of best fit, below, and then above the line of best fit. That tells me that when I have a line of best fit over here on this graph, it's going through in kind of a systematic way where I have points above, below, above. Okay, if you see curvature in your residual plot, that is an indicator that the fit of the original data is not that great for a linear regression, which is kind of what we thought in the beginning. We said in the beginning we did not really think this was a linear fit. We thought it was curved and it might be actually more exponential. The residual plot verifies that. Because I see clear curvature and or a pattern in the residual plot, that further backs up my suspicions that a linear fit is not necessarily the best fit for these particular data points. A linear fit is not going to approximate the overall pattern of this data. It's going to be going through it, and we're going to still possibly see a strong R value, but that doesn't mean it actually fits the pattern of the data. So do you think the regression line is a good fit for the data? The answer is no. And how do we know that based off the residual plot? The residual plot shows clear curvature. Which indicates the linear fit may not be best. All right, let's go to the next page. Let's get down some formal notes right here on linear regressions at least squares regression lines, okay? The definition of a least squares regression line is the line with the smallest sum of the residuals squared. Now we have to square those residuals because if we think about it, if half the data is above the line of best fit and half the data is below the line of best fit, which is what we're hoping for, then if I were to not square the residuals, when I would add the positive residuals and the negative residuals together, I would most likely get a sum of 0. So that's not really going to be helpful for us to indicate like how any type of actual measure of how well the line fits. So we square the residuals so that we can see the absolute vertical distance on the top and the bottom. The least squares regression line gets that line so precise that it is equidistant on both sides of this line. It keeps the sum of the residuals squared as small as possible. Okay, let's see. And let's get a formal definition down for a residual, okay? A residual is the vertical distance from an observed point to the predicted value or predicted point on the least squares regression line. So let's just talk about that really quick. Here's an example of a little scatter plot we've got right here. Let's say we have a line of best fit and some points. This is the residual, that vertical distance. Okay. Up here, I have a positive residual. A positive residual indicates an underestimate. Because if you notice, the spot on the line of best fit is underneath what actually occurred. We underestimated at that particular X value. This vertical distance is the residual. Because that point falls underneath the line, this is an overestimate. We estimated that value at this particular X value, something here, it fell underneath, it fell below, so that's an overestimate. As far as residual plots go, a plot with the residuals over here. These are positive residuals, these are negative residuals. All right, and these are our X values always. If I see a residual plot that looks like this, completely random, of course it's going to be different depending on how many data points we have, this is good. Okay, no pattern in the residual plot indicates a linear fit is appropriate for the data. Okay. If I have any kind of pattern in the resid plot, like what we saw, specifically curvature, this indicates bad, a poor fit. It doesn't mean there's no correlation. It just means a linear fit is not best, okay? So clear curvature indicates a linear fit is not the best fit for the data. Okay? All right, as soon as you get those notes down, pause this video, go ahead and try the you try options. And when you're done, unpause and check your answers. All right, so for this example, you should have calculated the least squares regression line right here, which we got. I put mine in context just to give you an example. And then below you were asked to make a residual plot. I always show what is happening in my lists just so that if I was getting graded, my teacher could see what I did. So in list 1, I put the X values. In list, which is body weight. List 2, I put the Y values, which is backpack weight. List 3, I put my regression equation, but instead of X, I plugged the entirety of list 1 in. Then in list 4, I did Y minus Y hat, which is list 2 minus list 3. I then plotted list 1 versus list 4 because the residual plot is always X values versus my residual values. And this is what the plot should have looked like. Okay, for question 3, it says, what does the residual plot indicate about the appropriateness of the linear model? Explain your answer. This one's a little bit hard to interpret. We could see it as random, or you could see it as having some curvature. There's not that many data points. So what would award you points here is consistent answers. Meaning, if you're saying that there's a pattern in the residual plots, you're telling me the fit is not great. Or if you're telling me it's completely random, you're telling me the fit is great. Sometimes, this is not the only indicator about how good a fit is. We've looked at a couple things so far. First thing to tell us how good fit is so far, we can look at the scatter plot itself. The second thing we can look at is we can look at the R value. And now we have another tool under our belt, which is the resid plot. So with all of these things together, we kind of get an idea about linear fit. But just looking at the residual plot alone, as long as the answer is consistent, if it's kind of ambiguous, that's okay. And later on, we're going to add like 2 more things to this list, which help us decide how good of a fit is it. And we'll use that to apply it to our final lab, which is our Barbie bungee jump. Okay, bye.